Hello learners, in this session we will be discussing about group 16 of periodic table. After the discussion, you will be able to appreciate occurrence of group 16 elements, differentiate between properties of group 16 elements, reason the exceptional behavior of first element of the group, describe general trends in chemistry of group 16 elements, explain the methods of preparation of oxygen, discuss properties of oxygen, discuss about simple oxides, explain the methods of preparation of ozone, discuss properties of ozone and appreciate uses of oxygen and ozone. Different elements present in group 16 are oxygen, sulfur, selenium, tellurium, polonium and livermorium. They are known as group of chalcogens. Oxygen is the most abundant of all the elements on earth, which is found in air, water and in minerals like oxides. Sulfur exists as sulfate and sulfides. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic material such as eggs, proteins, garlic, onion, mustard, hair and wool contain sulfur. Selenium and tellurium are also found as metal selenides and tellurides in sulfide ores. Polonium occurs in nature as a decay product of thorium and uranium minerals. Livermorium is a synthetic radioactive element. Its symbol is Lv, atomic number 116, atomic mass 292 and electronic configuration radon 5f14, 6d10, 7s2, 7p4. It has been produced only in a very small amount and has very short half-life. This limits the study of properties of livermorium. My dear learners, all members of this family tend to follow a general trend in properties. Let us discuss them one by one. The elements of group 16 have 6 electrons in outermost shell and have Ns2 Np4 general outer electronic configuration. Their size increases down the group due to increase in number of shells. As a result, ionization enthalpy decreases down the group. Ionization enthalpy of oxygen family is less than the corresponding element from group 15. This contradicts the general trend in a period. This is due to the fact that group 15 elements have extra stable half filled p orbitals electronic configuration. Electron gain enthalpy become less negative down the group, but oxygen has less negative electron gain enthalpy than sulfur. This is due to very small size and high electron density of oxygen. Oxygen is second highest electronegative element of periodic table and electronegativity decreases down the group. The metallic character of group 16 elements increases down the group. Oxygen and sulfur are non-metal, selenium and tellurium metalloids, whereas polonium is a metal. The melting and boiling points increases with an increase in atomic number down the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule O2 and sulfur exists as polyatomic molecule S8. The small size and less atomic weight of oxygen keeps its melting and boiling points lower than sulfur, which is bigger and heavier than oxygen. The common oxidation state of elements of group 16 is -2. Stability of -2 oxidation state decreases down the group as electronegative character decreases down the group. Other oxidation states of the elements of this group are +2, +4 and +6. Oxygen shows +2 oxidation state in its compounds with fluorine only. The stability of +6 oxidation state decreases down the group and stability of +4 oxidation state increases down the group. This is due to inert pair effect. The anomalous behavior of oxygen, like other members of p block present in second period, is due to its small size, high electronegativity. This is the reason that strong hydrogen bonding is found in water, which is not found in hydrogen sulfide. Now you can understand why water is liquid and hydrogen sulfide is gas at standard temperature and pressure. Actually, except water, all other hydrides are poisonous gases. The absence of d orbitals in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalence exceeds 4. For example, it can be 6 in sulfur. Let us understand how group 16 elements react with hydrogen, oxygen and halogens. Reactivity with hydrogen. Elements of group 16 react with hydrogen to form hydrides of the type H2E, where E is oxygen, sulfur, selenium, tellurium and polonium. The acidic character increases from water to hydrogen telluride, that is H2TE, due to decrease in bond enthalpy for the dissociation of hydrogen and E bond down the group. As a result, thermal stability of hydrides also decreases from water to polonium dihydride, that is H2PO. All the hydrides except water possesses reducing property and this character increases from hydrogen sulfide to hydrogen telluride. All hydrides have sp3 hybrid central atom with 2 lone pairs of electron on it. Let us discuss reactivity with oxygen. Elements of group 16 react with oxygen to form oxides of EO2 and EO3 type, where E is selenium, sulfur, tellurium or polonium. Both types of oxides are acidic in nature. Ozone O3 and sulfur dioxide SO2 are gases, while selenium dioxide SeO2 is solid. Since reducing property of dioxide decreases from sulfur dioxide to tellurium dioxide, sulfur dioxide is a reducing agent while tellurium dioxide is an oxidizing agent. Let us discuss about reactivity towards the halogens. Elements of group 16 form a large number of halides of type EX6, EX4 and EX2, where E is an element of the group and X is a halogen. The stability of the halides decreases in the order, fluorides being most stable, followed by chlorides, then bromides and then iodides. Amongst hexahalides, hexafluorides are the only stable halides. All hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride is exceptionally stable for steric reasons. Amongst tetrafluorides, sulfur tetrafluoride is a gas, selenium tetrafluoride is a liquid and tellurium tetrafluoride a solid. These fluorides have sp3 dehybridization and thus have trigonal bipyramidal structures in which one of the equatorial position is occupied by a lone pair of electrons. This is also regarded as seesaw geometry. All elements except oxygen form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well known monohalides are dimeric in nature. Examples are disulfur difluoride, disulfur dichloride, disulfur dibromide, diselenium dichloride and diselenium dibromide. These dimeric halides undergo disproportionation. Now, let us discuss about the first element of group 16, that is oxygen. Oxygen is colorless and odorless, which exists as diatomic gas in air. Oxygen can be prepared in laboratory by different methods, such as by heating oxygen containing salts such as chlorates, nitrates and permanganates, by the thermal decomposition of oxides of metals which are low in the electrochemical series and higher oxides of some metals, by decomposition of hydrogen peroxide into water and dioxygen in presence of catalyst such as finely divided metals and manganese dioxide. On large scale, it can be prepared by water or air. Electrolysis of water leads to the release of hydrogen at the cathode and oxygen at the anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapors, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Solubility of oxygen in water is low, but it is sufficient for the vital support of marine and aquatic life. It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen is unique in being paramagnetic in spite of having even number of electrons. Oxygen atom has 3 stable isotopes: oxygen 16, oxygen 17 and oxygen 18. If we discuss about chemical properties of oxygen, then it directly reacts with nearly all metals and non-metals except some metals like gold and platinum and some noble gases. Its combination with other elements is often strongly exothermic, but initially heating is required to break strong oxygen-oxygen double bond. Now, let us talk about uses of oxygen. It is important for respiration and combustion process. Oxygen is used in oxyacetylene welding, in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high altitude flying and in mountaineering. The combustion of fuels, for example, hydrazenes in liquid oxygen, provide tremendous thrust in the rockets. Let us talk about oxides. A binary compound of oxygen with another element is called oxide. Oxygen reacts with most of the elements of periodic table to form oxides. In many cases, one element forms 2 or more oxides. Oxides can be simple, for example, magnesium oxide, aluminum oxide, or can be mixed like oxides of lead and oxides of iron. Simple oxides can be classified on the basis of their acidic, basic or amphoteric character. The oxides which give acid with water are known as acidic oxides. For example, sulfur dioxide, carbon dioxide. For example, sulfur dioxide combines with water to give sulfurous acid. In general, only non-metal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character. For example, oxides of manganese, chromium oxide. The oxides which give a base with water are known as basic oxides. For example, calcium oxide combined with water to give calcium hydroxide, a base. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acids as well as alkalis. For example, aluminium oxide reacts with acids as well as alkalis. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Examples of neutral oxides are carbon monoxide, nitrous oxides and nitric oxide. Now, let us discuss about ozone, which is an allotrope of oxygen. At a height of about 20 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet radiations. Let us talk about preparation of ozone. When a slow, dry stream of oxygen is passed through silent electric discharge, conversion of oxygen to ozone takes place. The product is known as ozonide oxygen. Since the formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electric discharge in its preparation to prevent its decomposition. If concentrations of ozone greater than 10% are required, a battery of ozonizers can be used and pure ozone can be condensed in a vessel surrounded by liquid oxygen. Let us talk about properties of ozone. Pure ozone is a pale blue gas, dark blue liquid and violet black solid. Ozone in small concentrations is harmless, but when its concentration is above about 100 ppm, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen, since its decomposition into oxygen is highly exothermic and associated with an increase in entropy. So, these two effects reinforce each other, resulting in large negative Gibbs energy change for its conversion into oxygen. Therefore, high concentrations of ozone can be dangerously explosive. As it readily gives nascent oxygen, it is a powerful oxidizing agent. For example, it oxidizes lead sulphide to lead sulphate and iodide ions to iodine. Experiments have shown that nitrogen oxides combine very rapidly with ozone, and there is thus the possibility that nitrogen oxides emitted from the exhaust system of supersonic jet aeroplanes might be slowly depleting the concentration of ozone layer in upper atmosphere. Another threat to this ozone layer is probably posed by the use of freons, which are used in aerosol sprays and refrigerants. The two oxygen-oxygen bond length in the ozone molecule are identical, and the molecule is angular as expected with a bond angle of about 117 degree. If we talk about uses of ozone, it is used as a germicide, disinfectant and for sterilizing water. It is also used for bleaching oils, ivory, flour and starch. It acts as an oxidizing agent in the manufacture of potassium permanganate. After this discussion, we conclude that group 16 is oxygen family with electronic configuration NS2-NP4. Elements of group 16 generally show lower value of first ionization enthalpy compared to the corresponding elements of group 15. Oxygen is the most abundant of all the elements on earth. It reacts with nearly all metals and non-metals except some metals like gold and platinum and some noble gases. Simple oxides can be classified on the basis of their acidic, basic or amphoteric character. Ozone is protecting us from harmful UV radiations, but it is getting depleted by its reaction with freons and airplane exhaust that contain nitrogen oxides. Before we end this discussion, let me leave you with some assignment questions. Question 1. Elements of group 16 generally show lower value of first ionization enthalpy compared to the corresponding elements of group 15. Why? Question number 2. Write the order of thermal stability of hydrides of group 16 elements. Question number 3. Hydrogen sulfide is less acidic than hydrogen telluride. Why? Question number 4. Which of the following does not react with oxygen directly? These are zinc, titanium, platinum and iron. I hope you have understood the concepts discussed in this session. Take care.